Hi, I'm Bill Kuszmaul, and this talk is Closing the Gap between Cache-oblivious and Cache-adaptive analysis. When you have a machine that shares resources among multiple processors, you can encounter a phenomenon where, from the perspective of a given process, the amount of memory that's available to that process fluctuates over time. And as increasingly the kind of common computations are becoming more and more often on parallel machines, it's becoming increasingly the common case that memory fluctuations are a problem we have to deal with. Now, over the last 30 years or so, there's been a whole bunch of empirical work on this topic, designing heuristics that make it so that programs can handle memory fluctuations. But for the most part, these heuristics haven't come with provable guarantees. And so the line of research that I want to talk to you about today has been a more recent line of research that is focused on trying to design simple algorithms that have provable guarantees in this sort of situation. And to analyze these algorithms, we're going to use a variant of the disk access model. In the disk access model, you have a memory of some size m, and then any data that doesn't fit in memory has to be stored on disk. Data can then be written to and from disk in blocks of some disk block size b. That's the model, and because disk accesses are so expensive, the disk access model measures running time in terms of just the number of disk accesses that an algorithm performs. This ends up being able to accurately measure the performance of algorithms whose performance is bottlenecked by the degree to which that algorithm manages to utilize the memory given to it. Whereas the classical disk access model assumes that the amount of memory m is fixed. In the late 1990s, an extension of it was proposed known as the Cache-adaptive model. And in the Cache-adaptive model, it works exactly as in the disk access model, except now the amount of memory available can fluctuate over time. So the memory size m is now a function of time, and we call this function the memory profile. The question then becomes, how do you design simple algorithms that have provable guarantees in this model? And about 5 years ago, there were a bunch of kind of major breakthroughs on this. And they stemmed from this simple insight, which is that if our goal is to design optimally cache-adaptive algorithms, then maybe a natural way to do that is to first start with cache-oblivious algorithms and then reanalyze those algorithms in the cache-adaptive model. What makes cache-oblivious algorithms so promising is that these are algorithms that on one hand live in the disk access model, but on the other hand aren't allowed to be actually explicitly aware of the parameters b and m. And so the idea is that if we have an algorithm that already behaves well without knowing the underlying parameters of the cache, then maybe these same algorithms should also behave well if m fluctuates over time. And this direction of research has been hugely successful. Recent results have shown that a whole bunch of classic cache-oblivious algorithms are also optimally cache-adaptive. There's also another side to this, though, which is that it turns out there's also a large class of natural cache-oblivious algorithms that actually aren't optimally cache-adaptive. In fact, they're a logarithmic factor away from being optimally cache-adaptive. The algorithms that we're going to be focusing on are a certain natural class of recursive algorithms, a certain class of algorithms with a natural recursive structure. And before I describe what this recursive structure looks like, let me first say that really the focus of this talk is going to be trying to understand how real this logarithmic gap is or isn't. That is, should we be thinking of these algorithms as truly being a logarithmic factor away from cache-adaptive, or should we be thinking of these algorithms as being really essentially cache-adaptive on most natural memory profiles and then only on certain highly structured memory profiles and non-cache-adaptive? And in particular, what we're going to be doing is we're going to be applying techniques from beyond worst-case analysis in order to try to study this logarithmic gap. And we're going to be asking, does this logarithmic gap still exist if you apply, for example, smoothed and average case analyses. So that's what this talk is going to be about. And rather than trying to talk about an entire class of algorithms all at once, in order to make this more concrete, in this talk we're going to focus on a specific example, namely Strawsons' algorithm. Strawsons' algorithm is a simple algorithm for multiplying n by n matrices, and Strawsons' algorithm ends up being an example of an algorithm that is cache-oblivious but isn't cache-adaptive. The way that Strawsons' algorithm works is it has the following recursive structure. The algorithm first computes 7 recursive products of smaller matrices, and then the algorithm cleverly combines those results in a way so that it can compute the full matrix product that it cares about. And the result of Strawsons' algorithm having this natural recursive structure is that Strawsons' algorithm ends up automatically being optimally cache-oblivious. On the other hand, what Strawsons' algorithm doesn't end up being is optimally cache-adaptive. In fact, it ends up being a logarithmic factor away from being optimally cache-adaptive. And so the rest of this talk is really going to be in 2 parts. In the first part of the remainder of the talk, I want to dive into Strawsons' algorithm and understand why isn't Strawsons' algorithm, and other algorithms with similar recursive structures, why isn't Strawsons' algorithm optimally cache-adaptive? And then once we've done that, we're going to use tools from beyond worst-case analysis to try to understand to what degree this logarithmic gap is a phenomenon that we should expect to hold even on kind of real-world memory profiles. Okay, so to start off with, why isn't Strawsons' algorithm cache-adaptive? And when you're trying to understand the behavior of an algorithm in the cache-adaptive model, there's one tool that ends up making this a lot easier. This tool is what's known as a box memory profile. So in general, the memory profile that your algorithm might encounter can have arbitrary structure. But one really neat result that past researchers proved is that you can actually assume, without loss of generality, that the memory profile has a certain nice structure, which is known as being a box memory profile. A box memory profile is just a memory profile where the profile is a sequence of squares one after another. And you can think of a given square, for example, a square of some height k, as representing the memory profile giving your algorithm a memory of size k for time k, that is, for k disk accesses. And what memory profiles allow for you to, by assuming that your memory profile is a box profile, which it turns out you can do without loss of generality, it ends up becoming a lot easier to try to understand the performance of your algorithm. So let's try to understand Strawsons' algorithm, and let's start by focusing on a given box in our memory profile. So let's consider a k by k box in our memory profile, so that represents a cache of size k for time k. Let's try to understand, when we're running Strawsons' algorithm, what's the most progress that we could possibly hope for this memory box to make in Strawsons' algorithm? It turns out this single box in our memory profile could actually complete an entire subproblem of size roughly square root k by square root k. So we're multiplying matrices of size roughly square root k by square root k. The reason for this is that within a subproblem like that, the total amount of space that the subproblem requires is only roughly k. So this single box could actually load the entire subproblem into memory and then complete the subproblem without incurring any additional disk accesses. And that means that a k by k box is actually capable of completing quite a lot of work in Strawsons' algorithm. It can actually complete roughly k to the 1.4 memory accesses in the algorithm, where that ends up being the number of memory accesses that Strawsons' algorithm makes on a root k by root k matrix multiplication. So that's the good news. But then the other question that I want to think about for a second is, what's the worst case for a k by k box? What's the least progress that a box could, in our memory profile, could possibly make within Strawsons' algorithm? And it turns out the worst case for a box is that the time at which that box arrives in the memory profile is right after the recursive steps in a recursive subproblem Strawsons' algorithm, and right during the part of the algorithm where we combine together the results from those recursive steps. And if it turns out if that's when our box arrives, then what can end up happening is our box gets entirely consumed by just that little piece of the algorithm. That's just combining together the results from the recursion. And a consequence of this is that you can have a k by k box that actually only manages to make order k memory accesses of progress in Strawsons' algorithm. And this intuitively is why Strawsons' algorithm ends up not being cache adaptive, is that you can end up having boxes be positioned in such a way that they make much less progress than they should. And in particular, this suggests a very natural way to construct a worst-case profile for Strawsons' algorithm. You construct your memory profile recursively in a similar recursive structure to what Strawsons' algorithm has. First, you concatenate together 7 copies of smaller recursive memory profiles, and then at the end of that, you just paste a new box to your memory profile. And the idea here is that we're closely following the recursive structure that's already present in Strawsons' algorithm. And so this memory profile is designed so that this box is going to arrive exactly when Strawsons' algorithm finishes with these recursions and gets to the point where it's combining the results of the recursions together. And so what's going to happen is every single box is going to arrive at a point in time where that box is as least useful as possible. In particular, what this means is that we can actually have a box profile that does really poorly on Strawsons' algorithm, where Strawsons' algorithm makes as little, essentially does as bad as it possibly could on that box profile, even though those boxes had the potential to be making a lot of progress within the algorithm. That's why Strawsons' algorithm doesn't end up being optimally cache adaptive. Okay, so what happens if we then try to apply techniques from beyond worst-case analysis to Strawsons' algorithm and other algorithms with similar structures? This is where we get to kind of the main results of our paper. And the first thing to notice is that this worst-case profile that we constructed feels like it's kind of a rigid construction, in that what we're doing is we're placing boxes in exactly such a way so that those boxes appear at exactly the point in time where that box isn't useful. And it seems like if those boxes appeared even slightly earlier or slightly later, then the box could potentially make a lot of progress in Strawsons' algorithm. And so it seems like this is really a highly structured worst-case example. What this suggests is that maybe what we should be doing is we should be performing a smoothed analysis, where we randomly perturb the structure of the memory profile and see if that eliminates the logarithmic gap from cache adaptivity. The logarithmic gap away from cache adaptivity. And so in our paper, what we do is we perform 3 different types of smoothed analysis. And what we find are kind of surprising results. The first smoothed analysis that we try is we say, okay, what happens if we take our box profile, but then we randomly perturb the size of each of the boxes? We randomly multiply the size of each box by a random number between 0 and 1. And kind of remarkably, this actually doesn't eliminate the logarithmic gap. Even with this smoothing, you still have that Strawsons' algorithm is a log factor away from being optimally cache adaptive. So then we said, okay, well, what if we do something stronger? What if we try to really misalign the memory profile from the algorithm? And the way we do that is we make it so that the starting time of the algorithm isn't at the start of the memory profile, but instead it's at a random point within the memory profile. And so this is designed to really misalign the structure of the memory profile from the algorithm. But actually, remarkably, again, the logarithmic gap persists. We're still a logarithmic factor away from optimally cache adaptive, even with this form of smoothing. So then we said, okay, well, what if we do a really strong form of smoothing? What if we take our worst case box profile and we try to randomly kind of randomize the recursive structure of it so that it no longer aligns with Strawsons' algorithm? And in particular, we'll take our worst case our recursive structure of our worst case profile, but then instead of putting a new square at the end of the profile in each point of the recursion, we instead place the new square at the end of one of our 7 recursive subproblems at random. And we do that everywhere recursively within our our construction. So we totally randomize the recursive structure. And amazingly, again, this doesn't eliminate the logarithmic gap. Again, you have that Strawsons algorithm is still a log factor away from being optimally cache adaptive. And what's happening here is that actually this worst case memory profile is actually remarkably robust. In some sense, what's happening is we're having a cache alignment version of what's known as Peter's principle, the Peter principle. The Peter principle says that when an employee gets a job, they'll keep getting promoted until they get to a position that they're not good at, and then they won't get promoted anymore. And a similar thing is happening here. When the memory profile gets to a part of the algorithm that it does well on, it'll speed through that part of the algorithm until it gets to a part of the algorithm that it doesn't do well on, and then it'll slow down. And so, in essence, what's going on is the memory profile and the algorithm end up misaligning with each other in almost a pessimal way, in a similar way to what happens with the Peter principle. And so this got us to wondering, well, what happens if you just completely remove all recursive structure from the memory profile? And the way that we do this is we said, okay, suppose you take some original box profile, but then you construct a new one by making each of the boxes in your new profile be randomly sampled from the original profile. So you eliminate any recursive structure that might have been there. And now what's interesting is that this actually does eliminate the logarithmic gap. So if we do this form of average case analysis, we actually do now get a situation where our algorithms are cache adaptive. And not only that, but this holds no matter what the initial box profile is that you're sampling the boxes from. So this ends up being, in some sense, kind of the core technical result in the paper. It requires a whole bunch of interesting new combinatorial ideas. But because I'm kind of getting to the end of the talk, unfortunately, I'm not really going to have time to go into those ideas in this talk. But what I do have time to say is one kind of just concluding takeaway, which is this. The question that we wanted to ask in this paper was, how real is this logarithmic gap away from cache adaptivity? And what we found is kind of that it depends. It depends on what kind of randomness you have in your system, what kind of randomness you can expect from the memory profiles that you're going to encounter. If you have sufficiently much randomness, then the logarithmic gap actually does disappear. But if you have even a small amount of structure in your memory profile, then suddenly it's possible that you may actually still have that logarithmic gap. And so it really depends on what kind of structure you have within the memory profiles in your system. Thank you very much.